Wow, Nitty, we hope you're feeling better. We know that some colds are going around. Hope you feel better real soon. Tell you what, we're picking up with what we did yesterday. Yesterday we had this force, function. It's really a vector function, defining a vector field. And just like we did yesterday, we'd like to find that little f such that the gradient of that function f would equal our vector field function. So, what's the difference in what we're doing today? Well, we're going in one extra dimension. Yesterday, we just had x and y, I and j in our setup. Now we're going into 3D. And you could wonder, how do we adjust? Well, pretty easily, thankfully. We're going to say, look, here's our f. And we could say f is equal to the gradient of f. And you know what? We could even write it in a shortcut way. Here's y squared. Here's a 2xy plus e to the 3z. And then we could say here's our 3y e to the 3z. And my goodness, from here, what is that really saying? It's saying this. Remember what the gradient of f was all about. The gradient of f, wow, we're reviewing a lot of multi-calc today, aren't we? We're going back to just that gradient, just like we did yesterday, just reviewing that the gradient function is really a vector function of the partial derivatives of little f, right? So you could, in a heartbeat, say, look at your x component. Your x component was the partial derivative of f with respect to x. That's equal to y squared. And then you'd say, well, look in your middle component here, your j component. Well, that should be the partial derivative of little f with respect to y. And we have that. And then finally, we've got our partial derivative of f with respect to z. And that would be 3y e to the 3z. And given that we have these three partial derivatives of little f, the question is, could we find the original f? Yes, we could. Let's just start right here. Let's start with that very first setup, and we can say, wow, partial derivative of f with respect to x, we might want to work backwards and actually take an antiderivative with respect to x. Okay, one sec. So we're going to take an antiderivative. We know that the derivative of f with respect to x is y squared. So I'm going to take an antiderivative. Oops, this got messed up just a tad. So I'll say f is equal to, well, what's the antiderivative of y squared with respect to x? At y squared x or xy squared, right? But then you'd say, well, then you've got some constant. Now, wait a minute. This would be a constant really of a function of y and z. You see, remember that y and z, when we're taking derivatives with respect to x, we think of y and z as if they were constants, right? And when I'm writing g of y comma z, I'm allowing for the possibility that I might get a constant alone, like 7 or 3, but I'm also allowing that we could have y's and z's in the mix of that function as well. What won't be present, and please hear this, what won't be present in g are other forms of x, right? That's important later on. G right now is exclusively in terms of y and z, and it can involve constants like 7 or 14 or negative pi or whatever, but no x's. Anything with an x we already dealt with. And usually kids will say, okay, well, I guess I got that. I hope you did. Well, now what? We'll say, well, that's great, but now let's go to our next piece of the puzzle. We can say, I know what I get when I take my derivative with respect to y. So let's do that. I can do that with the problem that I just came up with. Partial derivative of f with respect to y. Now, what's the derivative of xy squared with respect to y? We'd get 2. xy, wouldn't we? And then you'd look right here, you'd say, whoa, how do I take the derivative of g, a function of y and z? Well, one way we could write it, here's a cute little way we could write it. We could say here's a g sub y, right? That's just saying I took the derivative of that function with respect to y. You could write, your deltas in there if you'd like. But you'd say, there it is. Now, all of a sudden, I hope someone's saying, but you know what that derivative really equals. You already know the partial derivative of f with respect to y. In fact, that came from the original form of the force function up there. And you could say, well, that was 2xy plus e to the 3z. Well, now I have an equation that I can deal with. And it doesn't take you too long to see that, wait a minute, I could very easily subtract a 2xy from both sides, right? You might as well just cancel them out, right? And then what? You could say, well, wow, I would really like to get g alone. You see, this is a derivative of g with respect to y. And doing the opposite of a derivative is taking an antiderivative, isn't it? So I'm going to take an antiderivative with respect to y. So I'll have g of y comma z. And I'm going to say, what's the antiderivative of e to the 3z with respect to y? And I think we'll all quickly say that it's y e to the 3z. And we could quickly take a derivative with respect to y to check if we did it right. But there's more. You could say, well, there could be a constant. Now, at this point, you could say, wow, a constant. In the past, last year, we'd always write a plus c. But remember here, if I were taking a derivative with g with respect to y, z would have been thought to be a constant, wouldn't it? So I'm going to say h of z. I'm going to say, look, you might have a constant like 8 or negative 3 or whatever it might be. But remember, z was thought to be a constant when we're taking derivatives with respect to y. So you might get a z showing up. Now immediately somebody can say, what about x? No. That's why I made such a big stink about the original function not having x in it. Right? The original function only could have a y or a z in it. And there you have it. Now, we can go right back up to our f and say, well, now I know a little bit more about f. In fact, I know a lot more about f. You see, f was xy squared plus that function g. Well, right now I could say, well, you know what? I can write it a little bit nicer, a little bit more informatively. That g is really y e to the 3z, and then I've got some function of z. Look at that. We doing okay? Of course, now the big question is you look at that last h of z and you'd say, wow, I wonder what that thing is. Well, it might be just a fixed number like 14. It might have some z terms in it. It might be 14z to the third or something like that, and then adding another constant. You'd say, well, wow, I wish I could find that. Well, there's one more piece of the puzzle that we have yet to take advantage of. We could take our partial derivative of f with respect to z. And let's do that. When we take our partial derivative of f with respect to z, wow, what's this xy squared when you take that derivative? That's just 0. What's the derivative of y e to the 3z with respect to z? Yeah, the chain rule. And then you got to say, well, wow, then I get that h prime of z. Notice we're down to a single variable. Ooh, that's nice. But then you'd say, now wait a minute. Did I not know what that partial derivative was? Yep, it was 3y e to the 3z. Bring that down right over here. You'd say, wait a minute, that sure looks familiar. You know, at the top of the page, we said, hey, our partial derivative with respect to z was that. Wow, we can cancel that out. What's left on the right-hand side? 0. Wow. So now I'm going to take my antiderivative of 0 with respect to z, and what do we get? Some constant. You could call it a c, you could call it a k. But guys, that's what that h of z really is. So, look, I'm going to go back to what we had earlier. And this is pretty much wrapping it up. We said, hey, this is it. Here's your f. And then we could say, well, plug in your h of z right now. And you've got x y squared plus y e to the 3z plus some constant k. That's your function of x, y, and z. How is that especially helpful now? You get a line integral, guys. You could just use the fundamental theorem for line integrals. Plug in your ending point into that function, minus plugging in your beginning point, and you can work out that line integral. Doing okay? All right, and that, my friends,